The goal of this session is to learn a little bit more about buffers, specifically how to calculate the pH of a buffer using the Henderson-Hasselbalch equation. So first question is, what is the Henderson-Hasselbalch equation? Here it is. pH equals pKa plus the log of the base form divided by the log of the acid form, concentrations. And so in other places you may see this written as A minus divided by HA. And the only difference there is just to remember that it needs to be the conjugate base form divided by the conjugate acid form. That's important. So the Henderson-Hasselbalch equation relates dissociation with pH. In other words, what is the ratio of A minus to HA and the pKa, and that'll tell us what the pH of the solution will be. When the pH equals the pKa for the weak acid, weak base pair, we see that the base concentration equals the acid concentration at equilibrium. And so if base equals acid, then A minus over HA will equal 1, and the log of 1 is 0, so pH will equal pKa. What that means is that you need to choose your weak acid conjugate base pair so that the pKa is within plus or minus 1 pH unit of the pH you want your solution to stay at. Okay, so not every weak acid conjugate base pair can buffer at every pH. Instead, those are the buffering pH is related to the pKa. And the reason for that is that when the pH is within 1 unit of the pKa, that means that the base to acid ratio will vary from 0.1 or 1 over 10 to 10 or 10 over 1. And so that pH range keeps a reasonable amount, an appreciable amount of both the conjugate acid form and the conjugate base form in the solution, which is important for maintaining the pH, as we talked about in previously. Okay, so you may wonder, where does the Henderson-Hasselbalch equation come from? Really, the Henderson-Hasselbalch equation is just a restatement of Ka, the Ka expression. So if we consider a weak acid in water, we know that it will dissociate to form the conjugate base form plus H3O+. And we further remember that the Ka for that reaction, that the expression, will be the H3O+ concentration times the conjugate base concentration divided by however much of HA we have at equilibrium. Okay, so maybe you remember that pKa is the negative log of the Ka. So if we do negative log of both sides, Ka equals negative log of H3O+ times A- divided by HA. Okay, then we'll see that this side equals pKa. And maybe you remember that if you have the log of x times y, that will equal the log of x plus the log of y. So we're going to separate this other side into negative log of H3O+ plus negative log of A- over HA. Okay, so negative log of H3O+, that's pH. So pKa equals pH plus, or maybe it might be better to write this as minus the log of A- over HA. Okay, so to get this into our familiar form, we just need to move this ratio term over to the other side, and then you'll see we get pH equals pKa plus the log of A- divided by HA+. Okay, so in other words, the Henderson-Hasselbalch equation comes from Ka. That's all it really means. It's just a rearrangement of that. Don't you wish that you had done a little bit of algebra and then put your name on the thing? All right, now a little bit of practice. If you wanted to prepare a buffer that would keep the solution pH at 9.3, which of these weak acids or weak acid-weak base pairs would you pick? The best choice here is D, boric acid and borate. And the reason we picked that is that the pKa is 9.24, which is close, within 1 pH unit, of the pH that we want our solution to be at. Okay, so now how could we calculate the pH of a solution we prepare? So here we have a buffer solution is prepared by dissolving 0.2 moles of NaH2PO4 and 0.1 mole of Na2HPO4 in enough water to make 1 liter of solution. And our question here is, what is the pH of this buffer? So our question is, what is the pH of the buffer? If you want to find the pH of a buffer, then your clue is you want the Henderson-Hasselbalch equation. pH equals pKa plus log of the base form divided by the acid form. All right, so in order to find pH, we're going to need to find the pKa and the concentrations of the base form and the acid form. So all of those things are related to the chemical reaction that's going on here. So our chemical reaction that is relevant is H2PO4 minus plus water is in equilibrium with HPO4 minus and H3O plus. Okay, so this is just the Ka2 reaction for phosphoric acid. And so I picked that one because I want something that has both H2PO4 minus and HPO4 2 minus. Sorry, let's fix that, 2 minus. And we see that that is the second dissociation of phosphoric acid, so it gets a Ka2. Okay, so that means that H2PO4 minus is the acid form, and HPO4 2 minus is the base form, and we have Ka. So if we want to find the concentration of the acid form, that's pretty easy here. We just do 0.2 moles divided by 1 liter, and the same for the concentration of HPO4 2 minus. That'll be 0.1 mole per liter. Okay, and to find pKa, we do negative log of the Ka that's given here, which is 6.2 times 10 to the minus 8. If you put that in your calculator, you get 7.21. Alrighty, so we kind of have everything we need in order to solve for the pH. So pH will equal the pKa, 7.21, plus the log of the base concentration, which is 0.100 moles per liter, divided by the acid concentration, 0.2 moles per liter. Okay, and so if I do that, I get 7.21 minus 0.30, if I do the log of that ratio. And so the pH of this buffer will be 6.91. Is that a reasonable number? Yes, it's reasonable because we have more of the acid form than we have of the base form in our mixture, so it's a little more acidic than the pKa, but it's still pretty close. Another way we could produce a buffer is to add some of a weak acid and a limiting amount of a strong base. So we'll do that here. So here is a similar but slightly different question, because you see here that instead of adding 0.1 mole of Na2HPO4 minus, we're adding some NaOH. So this is a different problem here. All right, here once again we're looking for the pH of the buffer, so we're going to need pH equals pKa plus the log of HPO4 2 minus divided by H2PO4 minus. Alrighty. So to find HPO4 2 minus and H2PO4 minus, we need to think about how the neutralization reaction between this acid and strong base becomes HPO4 2 minus plus water. Okay, and so then here's strong base. We know that the amount of OH minus is, so that when NaOH dissolves in water, it's going to form Na plus and OH minus completely. Okay. Also, this neutralization reaction between a weak acid and a strong base proceeds to completion. You notice there's no equilibrium arrows there. Okay, so we basically need to figure out how many moles of each thing we have. We start with 0.2 moles of H2PO4 minus, and we said we start with 0.1 moles of OH minus from the NaOH. So that means that the OH minus is the limiting reactant. So we're going to lose 0.1 moles of each thing in their stoichiometric ratios from each side. We start out with no HPO4 2 minus, but we're going to produce 0.10 moles. Okay, and so after the neutralization reaction, we're going to have 0.200 moles of, 0.1 mole, try again, 0.1 mole of H2PO4 minus and 0.1 mole of HPO4 2 minus. And so those are both going to be in 1 liter because it's in the same solution. So if we go back to pH equals pKa, we used to 7.21, plus the log of HPO4 2 minus is 0.1 molar, and H2PO4 minus is 0.1 molar. And so that means that the pH here will equal 7.21. Okay, so see there's 2 different ways that we can calculate the concentration or the pH of a buffer solution.